Well, good evening. Welcome. You are tuned in to AP Physics C, Electricity and Mechanics Live. And my name is Roger Siegel, and I'm coming to you tonight from Sarasota, Florida. As always, co-teaching with my friend, Kristen. Hey, Kristen.
Hello, Roger. Yes, my name is Kristen Gonzalez-Vega, and I teach at Reedy High School in Frisco, Texas. And Roger, I have to know, what is that behind you on that big Post-it note paper?
That thing up there?
No, on the Post-it note paper, the little
Oh
furry.
gosh, oh, these are what are these? These are seals.
Yeah,
Yeah,
seals.
one of my
Okay.
students said, would I bring the seals? They hadn't seen them, so I told her I was going to school, and she said, would I pick up the seals? And I said, yes. So now I'm going to make her watch this. All
Shout
right, well,
out.
we'll move that out of the way so it doesn't distract anybody. That's kind of huge. Thanks, Kristen. All right, well, let's move on to what we're here for again. So good to see you guys tonight. My name is Roger Siegel, and we are going to be talking tonight, working with you to get you ready for your AP Physics C exam. And so let's go ahead and get started on here. Okay, good. And tonight we are going to be talking about conductors, capacitors, and dielectrics, and particularly capacitors. That's what tonight is about. The whole unit is called conductors, capacitors, and dielectrics. Tonight we're just going to talk about capacitors. Tomorrow night will be about dielectrics, so you are going to want to tune in for that. So tonight, again, my name is Roger Siegel. I'm here at Sarasota, Florida, and working with Kristen Gonzalez-Vega from Reedy High School in Texas. We wanted to remind you that our exam time, depending on where you live, is going to be 1 hour only, and you have to be there for the whole time. You will do 25 minutes on the first question, and then you'll have 5 minutes to upload, and that's it. And then and that will be the window. And then after that, you will have 15 minutes to do the second question plus 5 minutes to upload, and that's it. And that's your whole AP exam. So please make sure you marked it in your calendar. We want to get you ready for that, and we have more coming in the future about that. Here's where we are this week. As you can see, we are, sorry, trying to make this work. This week we are working on conductors and capacitors, dielectrics tomorrow, and on Wednesday as well. And then we're going to start circuits, and circuits takes us all the way through the curriculum of AP Physics C. All right. Going down here, objectives tonight. I don't want to spend a lot of time reading them for you. You can come back and look. But really, everything is about learning about capacitors and capacitance and talking about what they are. And so that's going to be our guiding light. So let's talk first about what is a capacitor, because it's possible that you've never even heard of one, unless maybe sometimes, of course, as a physics teacher, people say, well, what about the flux capacitor? And that's from, of course, the movie Back to the Future. So not a flux capacitor, but we do study flux and we do study capacitors. But a capacitor is an object that usually goes in a circuit, but it doesn't have to. But what it does is it stores electric charge, and it has two conducting objects placed near each other but not touching. So usually what we'll talk about are two parallel plates being a capacitor. I'll show you a better drawing in a minute. But they don't have to be plates. They could, what a lot of capacitors are is they're two conductors that are not charging and an insulator in between them. And then what you do is you roll this up like a big roly-poly. And so you have this kind of sandwich where the two breads never touch, two pieces of bread, but it does create this capacitor. So what we do is, this is what a capacitor is. You have basically two plates. And what you do is you charge this up with a battery or a voltage source. And that's what our battery looks like. And you can see the difference between these. What does a battery do? Well, a battery pushes charges. It's like a pump for charges, positive charges, and it pushes them here. Now, positive charges, let's move on to the next slide, and then we'll draw this this down here. All right, so we've got this is a better picture here of our plates, and let's see what we're doing here. So our battery is taking positive charges and pushing them onto this metal plate. Okay. And can you imagine these two are going to be pretty close to each other in space? And so what's going to happen to any positive charges that are living on this plate? Well, they're going to try and go out of here as fast as they can. And what that's going to do is that's going to leave, since the positive charges have all left, it's going to leave this plate all negatively charged. Okay. And what that does is that creates in this space an electric field. Of course, the electric field, and this electric field, if these plates are pretty big, is uniform. It's the same throughout. Left, right, up, and down, it's the same. So that is what a capacitor is conceptually. Here is the roly-poly one that I showed you, and you can see that there's two plates that are separated by an insulator. And so that's another kind of capacitor. And so that's what a capacitor is. Let's go down and see some pictures of ones. Here's some capacitors, excuse me. Here's some capacitors that you might see in a circuit. If you looked into an electronics or a stereo or the back of a TV, you would see capacitors and working in what they do. And again, they're storing charge, storing energy in the electric field. Now, what is capacitance? Okay, well, it's how we measure a capacitor, how we compare them one to another. And capacitance is measured in farads. This is the unit. And so I want you to look at this relationship. This formula is one of those that's on your formula sheet. I hope you haven't ditched those formula sheets that we've been using all year. These are great. You want to keep using them, and we're going to add to them. All right. But this is the capacitance of a capacitor is equal to the amount of charge that you can push on it per unit voltage that you're pushing it with, right? So imagine I've got a certain voltage battery. If I've got a bigger capacitor, I can put more charge on that with the same battery. Okay, so the capacitance is actually like what it sounds. It's the object's capacity to store things, just like the capacitance of a cup or a tank. So this is a new unit for us, farads, F, and usually we'll do microfarads or nanofarads. Even picofarads, 10 to the minus 12, you can find those in electronics. These ones here, let's see, I think this one says 4205, and that should actually be a mu, but that's a microfarad there. So anyway, that's what we have, some of those. All right, let's take a look. So that's capacitance. Now, something about the capacitance of a capacitor depends only on its physical properties. It doesn't change its capacitance as you put more charge on it, okay? At least in our treatment of it. All right, parallel plate capacitor is the kind of capacitor that we're going to be talking about tonight. However, tomorrow night, we're going to do spherical capacitors and cylindrical capacitors, and these are also part of the AP curriculum. These are really going to challenge our concepts of geometry and how we look at the electric field, and we're going to look at Gauss's law again. We'll even look at that again tonight. All right, parallel plate capacitor, as we said, consists of two parallel plates separated by a distance D, and let's say that the plates have an an area A. This is the relationship. I should have had that a little bit bigger, so let's zoom in on it. It's a big one. This is important. This is the relationship that tells me what the capacitance is of this capacitor. And let's go through these. The A, of course, not of course, the A is the area in meters squared. The D is the distance in meters. Distance in meters, area in meters squared. Epsilon naught is the permittivity of free space. That tells us how easily an electric field can move through space. And then this number K over here, that is the dielectric constant, Dielectric. And that number for today is going to be 1 because we're not going to have a dielectric. So if you have air or if you have a vacuum between your plates, you can pretty much call your dielectric constant 1. Tomorrow night, we're going to, or either tomorrow night or Wednesday or both, we'll look at the dielectric constants that are not 1. All right. Now, I wanted to show you real quick a simulation that gets a really gives us a good idea of how this might look. And so let me pull this up and let me actually get this larger so we can fill the whole screen, even though we're only over here. Try and pull your attention here. So here we have a here we have our plates. Are let me see if I can do a double screen. Actually, I want to come over here. Okay, and let's open up this, and let's open up this, and let's see if we can do them side by side. Try it. Go Microsoft. Okay, that wasn't what I wanted. Oh, I think it is. Okay, good. All right, so let me come over here and okay. So I've got my simulation over here. Let's take a look. And it consists of a capacitor over here. Here's the capacitor. Okay. And I can change the area of the capacitor and I can change its separation. And those are the things, remember, the only things really that I can affect the capacitance of this capacitor, except by changing the dielectric, which we'll do in a few nights, as I said. So if I click on my capacitance meter, you'll see if I increase the area, that's going to increase my capacitance because I can store more charge per unit voltage. If I increase the distance, that will decrease my capacitor. The distance is, we know that C is equal to K epsilon naught A over D, and the distance is in the denominator, so when that gets bigger, the capacitance gets smaller. All right. If I start to push charges on here like this, I get now a positive plate and a negative plate. Vice versa, if I go the other way, I can push charges in this direction, but I'll keep pushing them this way. This makes sense. Now, if I change the size or the properties of my capacitor, notice that the charge on this will change. However, what will not change will be the voltage because I've got it hooked up to the battery. But if I disconnect it, now I've stranded the charge on there. Now the voltage can change and the charge cannot. And so that's something that you'll be looking at in a little bit. We'll look at with some of our problems tonight. All right, let's talk about this last thing before we want to try some of our problems to, see how we understand this. And that is the energy stored in a capacitor. And I said earlier that a capacitor stores energy in an electric field. It works kind of like a spring does in a mechanical system, believe it or not. It has some of the same functions that a spring has. But it stores energy. So we want to be able to calculate that energy. Now, that formula for that is given here. It's on your formula sheet. And these two are the formulas that are given. I'm adding this third one, which you could derive easily from the definition of capacitance, but is good to just have in your pocket, especially since this year we know that you have open book, open note, and access to all the formulas you want. A couple more things. If we put capacitors in series, they will add up like resistors in parallel. So they just behave the oppositely. And the charge on each plate is equal. So no matter what the capacitance is, the charges are the same. And you'll see how that plays out in a minute in one of the problems. Now, if we put the capacitors in parallel, we're going to add their capacitance. Remember, these formulas are all there on your formula sheet. And the voltage drop is now the same regardless of the capacitor. But what's different now is the charge. And so we want to try some of these problems tonight to give you a sense of what's going to go on. So I'm going to ask Kristen to go ahead and take it from here, and then we'll see how it goes. I'll do some more, and we'll have a great time at it.
All right, thanks, Roger. So let's look at a couple of what if situations, because we know that if we're going to be asked some conceptual questions, most likely on this year's exam, that you'll be explaining. And so we want to look at two different things that you can do, because you can charge up a capacitor. And I actually have a super capacitor. So yes, mostly we deal with microfarads. I have a 1 farad capacitor here. You can see how big that is. But so if we connect the capacitor, we can then disconnect our voltage source that we were using to charge up the capacitor and see how that behaves. Or we can keep it connected to our power supply and change the capacitor and see what happens. So we're first going to look at what happens if you have a charged capacitor. So we have a parallel plate capacitor. Let me go ahead and draw that off to the side here. And it is connected to a voltage source that has a voltage V0. And we are going to let this capacitor charge up, right? So we connect it to the battery, that current starts to flow. And as we get into circuits, we'll talk a little bit more about it, but it takes some time for that capacitor to fully charge up the plates. So we're going to wait until those plates are fully charged. They are going to have a charge Q0 on each one. Right? This one's going to be positive, this one's going to be negative, but the magnitude of that charge will be the same. And it is separated by a distance of d between those two plates. So what we want to do is we're going to disconnect it from the battery. So now we have just our 2 plates. Not only are we going to disconnect it from the battery, but we are going to increase that distance between them so that now it is 2d. So what I want to know is what happens to the capacitance of that capacitor, what happens to the potential difference across the capacitor, the charge that's on the one of those plates, and then also let's look at what would happen to the energy that is stored on that capacitor, right? So let's say our initial energy that's stored within that capacitor is mu0 or u0. Okay, so what happens to the energy, the charge, the capacitance, and the potential difference once we disconnect it from that battery, and then we separate it to twice the distance that it originally was. Okay, so there's a couple of things you want to keep in mind here. When it is disconnected from that battery, what that means is that whatever charge we had is all the charge we get, right? Because those charges that were being pushed out from the battery, now we don't have that kind of continual charge on there. So if we have this disconnected from the battery, then the charge that we had on there is conserved, right? We have conservation of charge. We can't gain more charge. The charge isn't leaving unless we then are going to discharge the capacitor. So our charge is going to stay the same. So when you disconnect the capacitor from the battery, we know that Q has to stay the same. So our new Q is going to be the same as the initial Q, or it's 1 time the charge. However you want to think about that. When it's disconnected, the charge is going to stay the same. Okay, so then we can look at what that's going to do to also look at what happens to the capacitance. So if the capacitance is equal to K times epsilon naught A over D, well, we didn't change what was between the plates. Obviously, epsilon naught's a constant. Did we change the actual surface area of each plate? No, that's all staying the same. So if we're putting a 1 in for all these things, well, if this is twice the distance, then this side's changing by a half, which means my new capacitance is now half of what the original capacitance was. Okay, and then we can look at the potential difference across those plates because we can relate the potential difference to the capacitance and the charge because we know that our delta V is equal to Q over C. So if we look at what we changed, our Q stayed the same. Our capacitance is now half as much. But if we have 1 divided by 1/2, that's really saying that we have twice the potential difference. Okay, and then what about the energy? What are we going to do to the energy? Well, Roger gave us a handful of different equations there. So let's use 1/2 Q delta V because my Q stayed the same. So let's pick an equation where I'm only going to have one thing that's changing. So if Q stays the same and delta V is now twice as much, well, that means we can store twice the original amount of energy that the capacitor stored when it was just D apart. So if you're removing it from that voltage source, then you're having the same amount of charge. It's kind of the immediate thing I want you to be thinking about. Okay, let's look at it the other way. Let's say that we keep it connected to the battery. So we have our same plates that we had just a minute ago. And initially when they're D apart, we store charge Q. Potential difference that it's connected to is V naught. And capacitance is C naught. Energy U naught. So what's going to happen if I keep it connected to the battery, but we change that separation distance to twice the original distance? So now the plates are 2D apart. What happens to all those things? So now I want you to think about what's going to stay the same and what's going to change. Okay, so if they're still connected to the battery, that power supply is the same. Well, what's got to stay the same? The voltage is going to stay the same. That potential difference across those plates is going to be the same as it was. So when it's connected up together, potential difference stays the same. When it's disconnected, charge is conserved and stays the same. Okay, so now let's look at again the capacitance because we know capacitance, not changing the shape of those plates or the geometry of those plates. I'm not changing the area. The only thing I'm changing again is the distance. So same case here. We have now 1/2 of the original capacitance. Okay, so if the voltage stays the same and we have half the capacitance, let's look at what's going to happen to the charge and the energy. Okay, if delta V is still Q over C, and we know our V stayed the same, that's a 1, we have half the capacitance. Well, the only way we're still going to get 1 is if I also have half the original amount of charge. Okay, and then again, let's look at what's going to happen to the energy. If energy is 1/2 CQ times V, and our potential difference stayed the same, but our charge is half as much, now I'm storing half as much as my original amount of energy that could store. Okay, so always be thinking about what's going to stay the same, what's going to change, what are those relationships, and how will that affect all of your variables. Okay, and I got one more here. Let's look at it now, an arrangement of capacitors. And we're going to do a lot more of this with circuits, but just to kind of get us thinking about how we combine these capacitors, we've got 3 capacitors here, a 12 microfarad capacitor, 2 and 4 microfarad capacitor. And if it's set up in this arrangement connected to a 12-volt source, let's determine A, what the total capacitance of this arrangement is, and how much energy would be stored total amongst the capacitors. So what are our steps here? What are we going to do first? How can we find the total capacitance of this, or the equivalent capacitance? We want to look at, are they in series or are they in parallel? Here we have a combination of both. So if I look at C2 and C3, that sticks out to me first. Those are in parallel. And then, so let's combine those first. Let's not get ahead of ourselves. So let's combine those two first. If they're in parallel, how do we combine capacitors in parallel? It's the opposite of resistors, right? So resistors in parallel, we have to do the inverse 1/. Capacitors, we simply add up. So the capacitance between 2 and 3 is just going to be my 2 microfarads plus my 4 microfarads, which gives me 6 microfarads. So it's almost like this now is one capacitor that has a capacitance of 6 microfarads. And that would be in series with my 12 microfarad capacitor. So how do we add those up in series? It's 1/, the total capacitance will be 1/, C1, which we'll call at 12 microfarads, plus 1/, my now 6 microfarads. So I can change my 1/6 to 2/12. That gives me 3/12, but that is 1/C. So C would be 1/, that, or would be a total of 4 microfarads. So in series, we have to do 1/C, add up all the inverses, and then in parallel, we can simply add them all together. So if we want to know if this has been connected for a long time, how could we find the total energy stored? Well, we can go back to that total energy stored and use any of those equations that we used before. So let's use for this one our 1/2 C delta V squared, because we don't know the charge on any of these, and we could find it and we could rake it. And I think that would be a good thing to try to think through, is which one of these capacitors would store the greatest amount of charge. Okay, and again, we'll get back to that a little bit more when we get to circuits. But I can plug in then that this is using our equivalent of 4 and our potential difference of our battery. Now that we are actually plugging in, we got to actually turn this into 4 microfarads is 4 times 10 to the negative 6 farads times our potential difference of 12 volts. All right, if we calculate that out, let's see. We get 2.4 times 10 to the negative 5th joules. Okay, so there's some practice for you. Roger is going to give us a little bit more practice for that AP exam.
All right, excellent. All right, folks, I got one more problem for us tonight, and I'm looking at the clock and I'm going, there's no way that this is going to take me 19 minutes. So we are definitely going to get out of here before 6:45 tonight. All right, let's go ahead and see what we've got. I'm going to bring you back to my screen here, and I want to look at a couple of problems here. All right, so let's pick up where we left off, where Kristen left us, and looking at, excuse me, charge on capacitor and what's going on with our come back. Okay, what's going on with our capacitor? All right. Okay, so we've got a parallel plate capacitor, charge Q plus on one plate and Q plus on minus on the other. By the way, these are always exactly opposite. They have to be. And the plates of each area are A and the distance D apart and separated by a vacuum. A single proton of charge E plus is released from rest at the surface of the positively charged plate, will arrive at the other plate with kinetic energy proportional to how much? So we want to know what its kinetic energy is. I'm going to draw this out because I think because I'm a physics teacher and I like to draw things. All right, it goes well with the drawing. So let's go ahead and draw this out. We've got and you should draw it with me if you can. We got a positive plate here, and we've got a negative plate here. Okay. And their charges are Q plus and Q minus. And we want to know what if we have a positively charged particle here, like a proton, all right, a single proton, not like a proton, it is a proton. It's released from rest here. How much kinetic energy does it have after moving this distance d through the vacuum? All right, and so it sounds to me like a conservation of energy problem. I hope you heard it that way too. And so we're going to set the energy change in potential energy, right, of our particle, electrical potential energy, is going to become kinetic energy. It's always good to think about what that is. And so if you recall, I hope you do, this is a couple of things. So we've said that this field is uniform. It's the same everywhere. So since it's the same, I can use a very, very simple approach to this and say this is Q and this is delta V. So whatever the charge is on here, not this capital Q, but this tiny little q. So let's let that be E delta V right away. And that's going to be equal to R delta K. Well, that's easy, but we want it in terms of everything else. What's delta V? Well, I learned also, we learned tonight that capacitance is equal to the charge on our plates divided by its charge per volt. It's coulombs per volt. And so that means that our delta V is going to be Q over C. And so I can, replace that. So that's going to be E Q over C. But then I look up here, and again, none of these have a C in them. So they're all in terms of something else. Well, what's the capacitance of a parallel plate capacitor? Well, I know that C is also epsilon naught. Well, it's K epsilon naught, but K is 1. Epsilon naught A over D. So I'm going to replace that. That's my delta K. I'm going to replace that. So I have E Q over C. And so the C is now epsilon naught A over D. And so if you remember, when we have something in the denominator of the denominator, that comes up front. And so we have EQD up top over E naught A. Well, I look at these and none of them have the E naught epsilon naught in it, but it doesn't say equal to, it says proportional to. So I'm going to just say, forget about you for a minute. Which one is it? And we look, it's right here. And so that's how we can look and see how we can get energy in that. Now, that's not a problem that's asking me how much energy is stored in the electric field. I want to be clear about that because we just talked about that a minute ago. This is not that problem, even though that's a good problem too. Don't confound the two. This is a different kind of problem that AP sometimes asks us to solve. All right, let's look at this last one for tonight. A parallel plate capacitor consists of two conducting plates separated by a distance d. In this case, notice they're using a capital D. The plates may be considered very large so that the effects of the edges may be ignored. The two plates have an equal but opposite surface charge per unit area. The charge on either plate resides entirely on the inner surface facing the opposite plate. On the diagram below, draw the electric field lines in the region between the plates. All right, so up here, this is very small, but I'm going to go ahead and circle it. This is sigma, this is plus sigma, and this is minus sigma. And remember, sigma is our charge density. That's going to be coulombs per meter squared. All right. All right. So I'm going to write that over here. This is my plus sigma, and this is my minus sigma. And I'll even remind myself about that they said these positive charges are all residing on the inside surface. So I'll draw that. And then what is my electric field? Well, the electric field is, the direction of the electric field is the direction of a positive test charge in that field. And so a force on a positive test charge would push it from the positive plate to the negative plate. And so that's what the electric field would look like. And remember, with a parallel plate capacitor, I have uniform electric field lines. Okay, now it says, by applying Gauss's law, let's see. By applying Gauss's law to the rectangular box whose upper surface lies entirely within the top conducting plate, as shown in the following diagram, determine the magnitude of the electric field E in the region between the plates. All right, now, I'm gonna draw this a little bit bigger because I think it will help us to see this, and I'm gonna draw it just straight on so that I'm not gonna worry about perspective. But here are my two plates, again, separated by this distance d. And they want me to use Gauss's law to find the electric field within this range, so within these plates. So let's do that. I'm going to draw a Gaussian surface that is a box. That's what they're asking me to do. And so I'm going to have this cube. And this cube is just, we're looking at it at the side here. We're not going to draw any depth to our cube, but it's a cube. So every side has a dimension A, and this dimension A is also evident here going back in the cube. And so if we ask, well, what is the, and remember the electric field lines are like this. They go from positive up to negative. So when I use Gauss's law and I say, what is the flux? Well, the flux is E dot dA vectors is equal to the enclosed charge divided by epsilon naught. So let's apply that. Well, once again, we can bring the E out because it is uniform and it is only penetrating, actually, it's only going through this surface. And so we're going to say the integral of dA, and that's going to be just the area of this bottom face, because the 5 other faces of this cube have no electric flux going through them. And so that's just going to be A squared. And over here, what we have is the enclosed charge. Well, if I look up here, how much charge have I enclosed? Well, the area of this face is A squared times sigma. That's going to be my charge. That's going to be A squared times sigma, because that's the charge density of my plate. So the charge density times the area gives me the charge. Coulombs per meter squared times meters squared, I end up with coulombs over epsilon naught. Well, this becomes one of the most boring algebra problems you've probably ever done in AP Physics C. And there it is. And so that's the electric field between those plates. Now, I would be remiss if I did not show you one other take on this that was shown to me by one of my favorite physics teachers. And it stuck with me, and I wanted to show it to you too. There's another reason that we can identify, really understand what that one is. And that reason has to do with this. Remember, you may not remember, but a few days ago, when we were working with Gauss's law, we said, what is the electric field due to a big sheet? Okay. And if you recall, that electric field, we said when we did Gauss's law, that electric field turned out to be sigma over 2 epsilon naught. All right. So if this is a positive plate, it has an electric field pushing out from it in all directions. And what was really interesting, I want to remind you about this, is notice that there's no D here. This doesn't matter how far I am from the plate. So it's everywhere in the, as far I want to be from the plate as possible. Remember, this is relative to the size of the plate. Now, this would be my negative plate, and a negative plate would have electric field lines pointing towards it like this, and they also would have an electric field of sigma over 2 epsilon naught. But you can see what would happen. This is pointing toward the the negative plate. And so let's add this up. Okay. And so if I come over here, one of the things we can see is that up here, the blue is all down, the red is up. They're going to add to 0. Same thing down here. We've got an electric field in this direction, electric field in this direction. They're equal in magnitude, opposite in direction. They cancel. And in this one, we have sigma over 2 epsilon naught superimposed with plus sigma over 2 epsilon naught. And that gives us sigma over epsilon naught. So E is equal to sigma over epsilon naught. Okay. Now the last thing, which will probably come up tomorrow, is this is also equal to V over D, the potential difference over that distance. So I just wanted to throw that one at you. That one is something that should show up pretty soon. All right, let's see. We hope that this has been helpful for you in understanding our capacitors. And so please stay tuned, because we're going to be doing some more capacitance work tomorrow night. Tomorrow night, we're going to do cylinders and spheres, and the geometry is awesome. You're going to love it. Kristen, are you going to take care of the spheres for us?
Yes, I also have one more thing. I forgot to square that potential difference. I'm going to go back just to show that real quick. I forgot to square the potential difference on my voltage in the energy equation. So it should be, sorry guys, 2.88 times 10 to the negative 4. But there's one more thing I wanted to add on, if I could piggyback off what you were just doing, Roger.
Yeah.
Let's find the capacitance between these two plates. Is that all right if I do that real quick?
Ooh, yeah, I love it.
Sorry, everyone. I'm going to hold you just a couple more minutes. It'll be real quick, but we're going to get that equation that we got at the beginning with this. So it's really cool. So we got that the electric field is sigma over epsilon naught, and we know that a relationship for potential difference. Let's find the potential difference between the two plates, the delta V here between the two plates. Because we did this last class, that the potential difference is the integral of the electric field. So if we do that, right, we're not finding the potential at one point. I just want to know between the two plates. So I can leave it as just delta V rather than having to pick two spots like we were doing the other day. So if we plug in then we get delta V is the integral of sigma over epsilon naught with respect to that distance. And if we integrate that, well, we've got this imaginary R in here to the 0, right? So when we integrate that, that becomes sigma times R over epsilon naught. But what is R between the two plates? It's D. So this becomes sigma times D over epsilon naught. So that's going to be the potential difference between the two plates. And so now let's turn that into capacitance, because from there it's easy, because if delta V is Q over C, what's C? Well, it's Q over delta V. So then C becomes Q over sigma times D over epsilon naught. You guys see where I'm going, right? The epsilon naught comes up, so this becomes Q times epsilon naught over. Well, let's plug in for sigma. If we're looking at the whole plate in itself, sigma is the amount of charge per area. So if we look at the total charge in that total area, then I'm going to put sigma is equal to Q over A times D. Well, what happens to the Q's? They cancel out. The A's 1 over 1 over comes up to the top, and we end up with sigma times A over D, which is what we got in the beginning. We have to add in that dielectric constant later, but that's just air. We're not going to worry about it tonight. All right. Thanks, Roger. I just wanted to add that in really quick.
No, I'm glad you did that, because that shows again how we can always circle back if we're consistent with our physics and we really are representing it correctly. We should get the same answer. And I love how that came back like that. So that's awesome. All right. Well, ladies and gentlemen, again, thanks so much for joining us tonight. It's been a pleasure to be able to share some physics with you, and we can't wait to do it again tomorrow night. Have a great night, and we will see you at 6 on Tuesday.